Imagine a weather model that tells you 80% chance of rain. For that number to actually mean something, it should really rain on about 80% of the days it makes that exact claim. When a model's stated confidence lines up with reality like that, across the whole range of probabilities it reports, we say the model is calibrated, and the calibration curve, sometimes called a reliability diagram, is how we check. This matters enormously anytime you use the probability itself to make a decision, not just the final yes or no label. Let's see how it works and why a model can be accurate and still get this badly wrong. Building the curve is a short, satisfying recipe. Follow it step by step. Start by binning the predictions. Gather all the times the model said roughly 10% into one group, then the 20% predictions into another, and so on across the whole range up to 100. Each bin simply collects together the predictions that share a similar level of stated confidence, which lets you check them as a batch. Within each bin, count what actually happened in the real outcomes. Among all the roughly 80% predictions, how often did the event really occur? If it landed about 80% of the time, that bin is honest. That observed frequency is your reality check against what the model confidently claimed. Then plot the two together. Put the average predicted probability along the horizontal axis and the observed frequency up the vertical one, placing exactly 1 point per bin. Connecting those points gives you the calibration curve itself, a simple visual summary of how trustworthy the model's confidence really is. Finally, compare against the diagonal. Perfect calibration is the line where predicted probability equals observed frequency exactly. So any drift away from that line flags a problem you can now see and quantify. The expected calibration error just sums up that gap across all the bins into one convenient summary number. Now here's a distinction people constantly miss. Calibration is not the same question as accuracy. Accuracy asks a simple thing. Is the final label right? A model can rank cases beautifully, cleanly separating positives from negatives with a high AUC, and score wonderfully here, while still being completely wrong about the actual probability numbers it attaches to each prediction. Calibration asks something deeper. Does the confidence match reality? A model can be perfectly accurate on its labels, yet wildly overconfident in its probabilities, and modern neural networks are notoriously so, cheerfully saying 90% when they turn out to be right only 70% of the time. That gap silently breaks any decision built on top of the numbers. So carry 3 ideas with you whenever calibration matters. First, the mechanics. Bin the predictions by their stated confidence. Then compare each bin's claimed probability against the frequency you actually observed in the real outcomes. That side-by-side comparison, repeated across every bin, is the entire heart of what a calibration curve is doing. Second, read the diagonal. The perfect line is where predicted equals observed. Points sitting below it mean the model is overconfident, and points above mean it's underconfident, so the shape tells you the direction of the error. Third, know when it bites. Any decision that weighs probabilities directly, medical risk, expected value, cost-based thresholds, or blending several models together, quietly breaks if the numbers lie to you. The good news is that Platt scaling and temperature scaling can rescale the outputs back in a line afterward, without retraining the whole model. All right, let's tie the essentials together. A calibration curve checks whether a model's predicted probabilities actually match how often the events happen. You bin predictions by confidence, then plot the average predicted probability against the observed frequency for each bin. Perfect calibration is the diagonal, dropping below it signals overconfidence, and rising above it signals underconfidence. Remember that this is a completely separate question from accuracy, and it becomes essential the moment probabilities start driving your decisions. For more clear, built-up machine learning breakdowns like this one, Standardy.com is where they all live.